Before we go 1 second further, subscribe right now because what you're about to discover will change the way you see every outlet, every power cord, and every light switch for the rest of your life. You've been told that electricity travels through a wire the way water moves through a hose. It sounds obvious, it feels obvious, and for most of us it became one of those facts we never thought to question. But that picture is incomplete in the most shocking way. The energy that lights a lamp is not simply being carried inside the copper by electrons racing from the power plant to your house. In the deeper and far stranger reality, the real action is happening in the space around the wire, and once you understand that, ordinary electricity starts to look almost supernatural. Let's begin with the familiar story because it exists for a reason. A battery is connected to a bulb. The bulb turns on, so we say the battery pushes electrons through the wire. The electrons move into the filament, and the filament heats up and glows. That explanation is simple, useful, and good enough for a lot of practical calculations. It helps you understand current, voltage, resistance, and power. It helps engineers design circuits that work, but useful is not the same thing as complete. The problem appears the moment you ask a very basic question. How fast do the electrons in a household wire actually move? Most people assume they must be moving incredibly fast. After all, when you flip a switch, the light comes on almost instantly. So surely the electrons must be blasting through the wire at astonishing speed. But when you do the math, the answer is almost comical. In a typical copper wire carrying a common household current, the average drift speed of the electrons is tiny, not just slow, tiny, on the order of fractions of a millimeter per second. In many everyday situations, an individual electron's net forward motion is slower than a snail. That means if one electron somehow had to make the full trip from a distant generator to your lamp by drift motion alone, it would take an absurdly long time. Not seconds, not hours, potentially years or centuries, depending on the path. Now yes, electrons inside the wire are moving rapidly in another sense. They're constantly jostling around because of thermal motion, bouncing in random directions at enormous speeds, but that motion is chaotic and cancels itself out. The actual organized drift in one direction, the part that counts as electric current, is extremely slow. So now we have a problem. If the electrons themselves drift so slowly, why does the light respond almost immediately when the circuit is closed? That question is the crack in the old picture. A common answer is to compare the wire to a tube full of marbles. Push one marble in at one end, and another pops out at the other end almost right away. In other words, the wire is already packed with electrons, so the signal moves quickly even if the individual charges don't travel far. That analogy helps a little, but it still misses something crucial. It explains why a disturbance can propagate fast, but it doesn't fully explain where the energy actually is and how it gets from source to load. To find that answer, you have to stop staring only at the electrons and start looking at the electromagnetic field. In the 19th century, James Clerk Maxwell brought electricity and magnetism together into one unified framework. His equations revealed that electric and magnetic effects are not separate stories. They are parts of one interconnected system. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. And together those fields can move through space as a self-sustaining wave. When Maxwell calculated the speed of that wave, he found the speed of light. That was the moment science realized light itself is an electromagnetic phenomenon. That discovery transformed physics. But it also forced a deeper question about something as simple as a wire carrying current. If electromagnetic fields can carry energy through empty space, then what happens around an ordinary circuit? A wire with a voltage across it produces an electric field. A wire carrying current produces a magnetic field. Those fields don't exist only inside the metal, they exist in the space around it. And if electric and magnetic fields coexist in the right way, they can transport energy. That is where the real story begins. A physicist named John Henry Poynting worked out the mathematical expression for electromagnetic energy flow. The result is what we now call the Poynting vector. It tells you the direction energy is moving and how much of it passes through a given area each second. When you apply that idea to a current-carrying wire, the result is deeply counterintuitive. The energy does not primarily stream down the middle of the wire like cargo in a tunnel. Instead, the energy flows through the electromagnetic field in the space surrounding the wire, and then moves into the resistor, lamp filament, or motor where the energy is used. That means the wire is not best understood as a pipe full of traveling energy. It is better understood as a structure that guides the field. This sounds outrageous the first time you hear it because we are trained to treat empty space as empty. But in electromagnetism, the space around conductors is not an inactive void. It is where the energy resides and where the energy moves. Think of a canyon guiding a river. The rock walls shape the path, but the water does not flow through the rock. It flows in the open space between the walls. In a similar way, the conductors define the geometry, but the energy travels in the electromagnetic field around them. The wire matters enormously, but not because it's a little pipeline full of electrical fuel. It matters because it creates the conditions that let the field organize itself and deliver power where it's needed. There is another piece of this puzzle that rarely gets much attention in beginner explanations: surface charge. In a real circuit, tiny imbalances of charge accumulate along the surface of the conductors. Those charges are not random. They arrange themselves in just the right pattern to establish the electric field along the circuit. That field extends outside the wire as well as inside it. Combined with the magnetic field created by current, it determines the direction of energy flow. So even though the amount of charge involved is extremely small, those surface charges help shape the entire electromagnetic landscape of the circuit. This is why flipping a switch is not just about electrons beginning a long march. It is about the electric field reorganizing throughout the circuit at nearly the speed of light in the surrounding medium. That change in field structure is what tells the entire system how to behave. The electrons respond, the current develops, the magnetic field appears, and the energy begins flowing through the field toward the load. Now let's make this even more dramatic with a thought experiment. Imagine a battery and a bulb placed just a few feet apart but connected by wires that stretch absurd distances away before eventually looping back. Suppose the total wire length is hundreds of thousands of kilometers. If energy had to follow the copper path all the way around at the drift speed of electrons, the bulb would sit dark for a ridiculous amount of time. But that is not what happens. The moment the switch closes, the electromagnetic disturbance begins spreading outward. The bulb, being physically nearby in space, can begin receiving energy from the changing field very quickly, long before steady-state conditions are established throughout the full wire loop. The full brightness may take longer as the entire system settles, but the crucial lesson remains: the field delivers the influence first. This distinction becomes even more important in alternating current. In your wall outlet, the electrons are not steadily marching from the power plant into your appliances. They mostly oscillate back and forth over tiny distances. They wiggle. They do not make a one-way cross-country trip into your toaster, yet your toaster still heats up, your lamp still shines, and your charger still powers your phone. If you cling to the idea that electrons themselves are carrying the energy from far away, alternating current becomes hard to picture. But once you recognize that the energy is transported by the field, the confusion disappears. The electrons move locally. The field transfers energy globally. This is also why antennas work. In a transmitting antenna, charges oscillate back and forth. That changing motion produces changing electric and magnetic fields, and those fields detach and race away as electromagnetic waves. The energy leaves the antenna and crosses open space with no wire at all. Far away, those fields reach a receiving antenna and push charges there into motion. Radio, television, Wi-Fi, and mobile communication all rely on the same fundamental truth. The field carries the energy and the information. Transmission lines make this even clearer. In a coaxial cable, for example, the energy is concentrated in the space between the inner conductor and the outer shield. That region may look empty, but it is where the electromagnetic field lives. The metal surfaces serve as boundaries that guide the field cleanly and efficiently. In that sense, the engineering of a cable is really the engineering of the field geometry. The dimensions, spacing, and dielectric material matter because they control how the electromagnetic energy propagates. Once you see this, a lot of technology starts making more sense. Waveguides, microwave systems, high-speed digital lines, RF design, and even electromagnetic interference are all field problems first and wire problems second. The old electricity flows through the metal like fluid in a pipe image is too crude to explain them properly. Now, none of this means the wire is unimportant. That would be swinging too far in the other direction. The wire is essential because it allows charges to move, and that motion helps establish the magnetic field. The material properties of the conductor also matter because resistance determines how much energy is absorbed as heat. In an ordinary resistor, the energy flowing in the surrounding field is directed into the material, where it becomes thermal energy. In a nearly lossless conductor, much less energy is dissipated. In a superconductor, the picture changes again because resistance vanishes and the field behavior becomes even more subtle, so matter still matters. The point is not that conductors are irrelevant. The point is that the familiar story assigns the role of energy carrier to the wrong thing. The deeper truth is that charges and fields work together. Charges establish and respond to fields. Fields store and transport energy. The conductor shapes the route, but the field does the delivery. There is something beautiful about that. It tells us that the invisible structures of physics are not mere bookkeeping tricks. The electromagnetic field is not just a mathematical convenience drawn in textbook arrows. It has energy. It has momentum. It can exert pressure, carry information, and move power from one place to another. In that sense, the space around a wire is alive with physical activity, even though our eyes detect none of it. And maybe that is the most fascinating part of all. Everyday life trains us to notice the solid object and ignore the emptiness around it. We trust the copper, the plug, the lamp, the battery. But in electromagnetic systems, what appears to be empty space is often where the most important events are unfolding. The unseen region around the conductor is where the energy is organized, guided, and transferred. So the next time you switch on a light, don't imagine tiny particles sprinting heroically from a distant power station to your bulb. Picture something more elegant. Picture a rapid reshaping of electric and magnetic fields throughout the circuit. Picture the surrounding space filling with directed energy flow. Picture that energy converging on the lamp filament, pouring into it from the electromagnetic field around it, heating it until it glows. The electrons are involved, absolutely, but they are not little delivery trucks hauling packets of power down the copper. They are part of a larger choreography, and the field is the medium through which the energy truly moves. That is why the simple story is taught first. It is easier, and for many practical tasks, it works well enough. But if you want the deeper view, the one that connects household circuits to radio waves, to transmission lines, to modern communications, and to the real architecture of electromagnetism, then you have to let go of the pipe analogy. Electricity is not just about charges inside matter. It is also, and more profoundly, about fields in space. The shocking twist is that the most important part of a circuit may be the part you cannot see. Not the copper itself, but the invisible electromagnetic structure wrapped around it. Not the wire alone, but the field it sustains. What looks like nothing is not nothing at all. It is a dynamic, measurable energy-carrying part of reality. And if we could actually see that energy flow with our own eyes, a simple lamp cord would no longer look simple. It would look like a glowing channel of directed power in the air around the conductor, with energy streaming through space and diving into the filament where light is born. It would look less like plumbing and more like a hidden river of physics flowing all around us, every hour of every day. That is the real wonder here. The familiar world is stranger than it appears. Your walls, your outlets, your cables, your chargers, your appliances, all of them are participating in an invisible drama of fields and forces. The room may seem still, but the space around every energized wire is active, structured, and busy carrying power. If this changed the way you think about electricity, hit like, share your thoughts in the comments, and subscribe for more deep dives that reveal the hidden physics behind the ordinary world.